Hello students and welcome to the quick solution of All India Cast Test Series JEE Advanced 2020 Test 3A Paper 2 Code GNH Physics. Let's move to question number 1. In question number 1, an ideal gas undergoes a cyclic process as shown in figure. The temperature at point A is T0. The maximum temperature attained by the gas is. So if I see here, the temperature at point A is T0 and it is an isochoric process. So in this isochoric process, as pressure is proportional to temperature, so the temperature will increase in this process. So the temperature at point B is greater than at point A. In process C2A, as the process is isobaric and the volume is decreasing, so the temperature will decrease. So it means the temperature at point C is greater than the temperature at point A. Now I have to find out the condition of temperature between B and C. So in order to find out this, I am writing the equation of pressure versus volume. So that can be written as P is equal to slope of this straight line is minus P0 by V0 into V plus intercept on y-axis is 4P0. So this is the equation between pressure and volume. Since it is an ideal gas, so we know that PV is equal to nRT. So by replacing P, we can write nRT by V, that can be written in this way, minus P0 by V0 into V square plus 4 times P0 into V. So if I differentiate this equation with respect to volume and substitute it is equal to 0, then we will find that V equal to 2V0 at which the temperature is maximum. So if I calculate the maximum temperature, then T max is the midpoint of process BC. So that can be written as 2P0 into 2V0 divided by nR, and we know that the temperature T0 at point A can be given by P0 V0 by nR. So this can be written as 4 times T0. So option B is the correct answer. Let's move to question number 2. In question number 2, 1 mole of an monatomic ideal gas at initial volume V0 and temperature T0 is heated through a process whose molar heat capacity is 2R, where R is universal gas constant. If volume of gas becomes 2V0 during the process, then final temperature of gas is. From first law of thermodynamics, we know that dQ is equal to du plus dW. We know that the value of dQ is given by NCDT. So 1, the value of C is 2R into dt. The value of du is NCVDT. So 1 into CV for a monatomic gas is 3R by 2 into dt, and dW is given by P into dV. So we can get P dV is equal to R by 2 into dt. Now for 1 mole of an ideal gas, we can say P into V is equal to 1 into RT. So if I replace the value of P, then this can be written as dV by V into 2 is equal to dt by T. So on integrating from T1 to T2 and from V1 to V2, we will get 2 times ln V2 by V1 is equal to ln T2 by T1. So from this we can write T2 is equal to T1 into V2 by V1 whole square. Now in the question it is given that the volume of gas becomes 2V0. So V2 is 2V0 and V1 is V0. So their ratio is 2 and its square is 4. So this can be further written as T1 is T0 into V2 by V1 is 2. So we can write this is equal to 4 T0. So option C is the correct answer. Let's move to question number 3. In question number 3, a container is filled with an ideal gas at temperature T0. Now the inner surface of the container is maintained at temperature T. When T is less than, equal to or greater than T0 and greater than T0, the corresponding pressure of gas are P1, P2 and P3 respectively. Then let's analyze the situation. Suppose this is the container which is filled with an ideal gas. So this is the gas and this ideal gas is at temperature T0. Now the inner surface of the container is at temperature T. So we can say that for this ideal gas, PV is equal to nRT, and for this ideal gas contained in the container, V and N are constant, so P is proportional to T. So the final pressure of the gas is proportional to the final temperature of the gas. And final temperature of the gas in a steady state is equal to the temperature of the inner surface of the container. So when T is less than T naught, the pressure of the gas at that instant is at P1. When T is greater than T naught, so the pressure at that point is T2, which is greater than P1. And when T is greater than T naught, the pressure is P3, which is further greater than P2. So this is the relation. So option C is the correct answer. Let's move to question number 4. In question number 4, for the given arrangement, the time period of oscillation is. So we can see that these two springs is in series combination with respect to the given arrangement. So we know that the time period of a spring lock system is 2 pi under root m by k equivalent, and the k equivalent in this case is given by 2k into k divided by 3k. So this is equal to 2k by 3 in case of series arrangement. So the time period is given by 2 pi under root m by k equivalent. So k equivalent is 2k by 3. So option B is the correct answer. Let's move to question number 5. In question number 5, a hollow spherical conductor has inner radius r and outer radius 3r. Thermal conductivity is same everywhere. The inner and outer surfaces are maintained at temperature 100 degrees Celsius and 40 degrees Celsius respectively. The temperature of the spherical layer of radius 2r in a steady state is. So in order to calculate the temperature of the spherical layer of radius 2r in a steady state, first of all I am analyzing what is the thermal resistance of the given spherical conductor. So in order to calculate this, suppose I am considering a spherical conductor at a radius r of thickness dr. So the thermal resistance of this considered element can be written as dr is equal to rho, that is 1 by k, let k is the thermal conductivity, into L, that is dr, divided by area, that is 4 pi r square. Suppose if I calculate the effective resistance from R1 to R2, so R is equal to integration of dr from R1 to R2. So if I integrate this, it comes out to be 1 divided by 4 pi k into R2 minus R1 divided by R1 R2. Suppose T is the temperature of the spherical layer of radius 2r in a steady state, then we can write 100 minus T divided by thermal resistance of 1, that is from R2 to R, is equal to T minus 40 divided by R thermal of 2, that is from 2R to 3R. So if I calculate the thermal resistance 1, that is equal to 1 divided by 4 pi k into 2R minus R divided by 2R into R. So on solving, it comes out to be 1 divided by 8 pi kr. Similarly, if I calculate R thermal 2, that is equal to 1 upon 4 pi k into 3r minus 2r divided by 3r into 2r. So on further solving, it comes out to be 1 divided by 24 pi kr. So we can say that this is equal to 3 times R thermal of 2. Now if I substitute this, 100 minus T is equal to 3 times R thermal 1 is equal to T minus 40 divided by R thermal 2. So on solving, the value of T comes out to be 55 degrees Celsius. So option C is the correct answer. Let's move to question number 6. In question number 6, a particle moves along x-axis such that its velocity v varies with time t as v equal to 10 cos pi t meter per second, where t is in seconds. At t equal to 0, the particle starts moving. The distance traveled by this particle in first 4.5 seconds is. So if I calculate the time period of this motion, then time period is given by 2 pi by omega. So on comparison, the value of omega is pi. So it comes out to be 2 seconds. Now we know that the velocity at mean position is maximum. that is given by a into omega, and we can see from this equation the maximum velocity possible is 10 meter per second. So if I calculate the value of a, the value of omega is pi, that is equal to 10. So the amplitude of this motion comes out to be 10 by pi. Now I have to find out what is the distance traveled by this particle in first 4.5 seconds. Since we know that the distance traveled in 2 seconds is 4a, so the distance traveled in 4.5 seconds is 9a. So if I substitute the value of a, that is 10 by pi here, it comes out to be 90 by pi meter. So option D is the correct answer. Let's move to question number 7. In question number 7, a uniform semicircular disk of mass m and radius r is suspended through point O. The time period of small oscillations in plane of disk is. So this is an example of physical pendulum, and the time period of physical pendulum is given by 2 pi under root I divided by mg into d, where I is the moment of inertia of the given rigid body about this point. So I can be written as mr square by 2 of this rigid body about point O, and the center of mass is at a distance of 4r by 3 pi in the case of semicircular disk. So the value of d is given by 4r by 3 pi. So if I substitute here, this is equal to 2 pi under root, the value of I is mr square by 2 divided by mg into d, that is 4r by 3 pi. So on further solving, it comes out to be pi into under root 3 pi r divided by 2g. So option C is the correct answer. Let's move to question number 8. In question number 8, two spring block systems are arranged on a smooth surface as shown in figure. The spring 1 is compressed by length A and spring 2 is in natural length at given position. If collisions are elastic, then time period of oscillations when block A is released. It means that in given situation, the block A is already compressed by distance A from its natural length. So we can see that the blocks are of equal mass. So when this block comes to this position by gaining some velocity, this velocity gets transferred to block B and the block A comes to as the collision is elastic. So thereafter we can say that this block will move in this direction and come back to this position again, and again it have an elastic collision with block A. So we can say that the time period of this given motion can be written as, let the time period of this spring block system is T1 and the time period of this spring block system is T2. Then the time taken by block from this position to this position is T1 by 4. Then this block B will move in this direction and again it will come here. So T2 by 4 plus T2 by 4. Then again this block A will move from here to here. So we can say that the time period of this is 2 times T1 by 4, that is T1 by 2, plus 2 times T2 by 4. Again it is T2 by 2. So if I substitute the value of T1, the value of T1 is 2 pi under root m by k, and the value of T2 is 2 pi under root m by 4k. So if I substitute the value of T1 and T2 here, then we will find that this comes out to be 3 pi by 2 under root m by k. So option A is the correct answer. Let's move to question number 9. In question number 9, a thin plank of mass m and length L is placed symmetrically over a fixed cylinder of radius r as shown in figure. Find time period of small oscillations when one edge of plank is pressed down slightly and then released. Friction is sufficient to prevent slipping. So in the question it is given that the cylinder is fixed. Suppose this plank is rotated by small angle theta. So we can say that this is the situation. this plank is tangent to this fixed cylinder. This is the point of contact. So at this point of contact, let this center of mass moves to this position, and the mg is acting vertically downward. Since this angle is very small, so we can say that the position of center of mass is close to this vertical line. So if this angle is theta, this is a very small angle, then we can say that this perpendicular is r sine theta, or theta is very small, then the length of this perpendicular is r into theta. So about this point of contact, if I write the torque equation, then friction and normal are passing through this point of contact, their torque is 0. So the restoring torque is of the gravitational force acting on the plank. So we can write mg into r theta is equal to I about point of contact. So that can be written as ml square by 12 into alpha. That is the restoring angular acceleration. So if I calculate the value of alpha, that comes out to be 12 gr by L square into theta. So on comparison, we will get the value of omega. So the time period can be written as 2 pi by omega, and the value of omega is under root 12 gr by L square. So this can be written as L square divided by 12 gr under root. So if I solve this, it comes out to be pi into L divided by under root 3g into r. So option D is the correct answer. Let's move to question number 10.